Hello everyone, we're talking about alternating series today. Alternating series is any series where you alternate signs. So you start positive, then negative, positive, negative, or vice versa. You start negative, go positive, negative, positive. Okay, now typically you'll be able to tell that is alternating right away because of this right here. You'll have -1 to some power. Okay, but don't be confused if you also see something, for instance, like cosine of pi n. Okay, that will also give you an alternating series. Because if you think about it, if you plug like 0 in for n, cosine of pi is positive 1. Sorry, negative 1. If you plug 2 in, cosine of 2 pi is 1. And then 3 pi would be -1. Then, okay, so something like this, a trig function can also give you alternating series as well. Right? So it's not always just with a -1, but a lot of the time it will have this. Okay, now figuring out if these converge or not is a little bit different. Okay, it's a three-step process. Okay, and there's three things we want. We want it to alternate in sign, and you're just going to prove that by writing out some terms and showing that it alternates in sign. Okay, you want the terms to decrease in magnitude, meaning that the absolute value of each of your terms needs to be getting smaller, and the nth term test needs to give you a limit of 0. Okay? Now, the interesting thing is, if you do the nth term test and you do not get 0, then it diverges just by the nth term test. Okay, now if you take the nth term test and it does give you 0, just with alternating series, if these other two things are true, then it does converge. All right, so let's run through that. Okay, now real quick, this is an interesting example. So I would say the first thing I would do again with any series that I get is to do the nth term test. Okay, with any series that really should be the first thing that you do. So if I do the nth term test, so I take the limit as n approaches infinity, absolute value, -1 n plus 1 n over 2n minus 1. Okay, so this absolute value negates this alternating stuff. Okay, if I take the limit to infinity, essentially again, of n over 2n minus 1, I get 1/2, okay, which is not 0. So this is divergent by the nth term test. And that's why you should always do the nth term test first, because a lot of times it'll save you extra work. Hey, you don't have to go through and prove those first two things for the alternating series test, and then get to the third part and see, oh, it was divergent anyway. Okay, so always try doing the nth term test first just to see what happens. If you get 0, then try something else or move on. Okay, if you do not get 0, you can stop right there because it's divergent. All right, now let's do another example. Okay, so what I'm going to do is write out a couple terms. So I'm going to plug in 1. So if I plug in 1, I get -1 over 1. Okay, and if I plug in 2, I get plus 1 over 4. Okay, if I plug in 3, minus 1/9 plus 1/16 minus ... Okay, so here's some things I observe. First of all, it's clearly alternating in sign. So I'm going to state that. So it's alternating in sign. Okay, I see it goes minus, plus, minus, plus, minus. Okay, I see that's going to do that. Secondly, I'm going to compare the absolute value or the magnitude of my terms. So I start with 1, and this is greater than 1/4, which is greater than 1/9, which is greater than 1/16. Okay, I see that my terms are, I don't know what's doing. All right, I see that my terms are decreasing in magnitude. All right, so you could say like a sub 1 is less than or equal to a sub 2, which is less than or equal to a sub 3. And so on. Okay, this is just what I'm trying to prove. I'm trying to prove that each of my subsequent terms are smaller than the last. All right, and I see that. I see that that's true, so I'm good. All right, and then the third thing I have to do is evaluate the limit as n approaches infinity, which I see that, again, remember these absolute value bars make the alternating part go away. So if you plug infinity in here, it does approach 0, so that's good. So 1, 2, 3 check marks. I can say that this is convergent by the alternating series test. Okay, so for the alternating series test only, you have these three things that you have to check, and you have to check all three of them, show them explicitly. All right, let's keep going. All right, so this is just a graphic showing what happens in an alternating series and why it can converge. So you see that it keeps bouncing, and it does get closer and closer to this final solution here, okay, to our final sum, is what the S stands for. Okay, now we have a couple more things. All right, so we say that our summation is absolutely convergent if both the absolute value of our sum and if our original sum both converge. Okay, so this particularly for alternating series. Okay, if the alternating series converges, and also if you take away the alternating part and it also converges, it still converges, then it's called absolutely convergent. Okay, conditionally convergent is if one of them converges and the other one doesn't, essentially. Okay, so an example of conditionally convergent would be 1 over n, for instance, or the alternating harmonic series and then the regular harmonic series. That would be an example of conditionally convergent, but we're going to run through a different one right now. Okay, so here, first let's prove that it's convergent, that just the function that I'm given is convergent. Okay, so we'll write out a couple terms. So your first term is -1, 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, 1 over the square root of 5. Okay, so here are the things that I notice. First of all, it is definitely alternating in sign, so that gets a check mark. All right. Now, are my terms decreasing in magnitude? Well, 1 is definitely greater than or equal to 1 over the square root of 2, which is definitely bigger than 1 over the square root of 3, which is definitely bigger than 1/2. Okay, so that gets a check mark as well. And if I evaluate the limit to infinity of the absolute value of my function, so this is n to the 1/2, okay, you do get 0, so that's a check mark. So this is convergent. Okay, this alternating series is convergent. Now, if I want to check if it's conditionally convergent or absolutely convergent, I evaluate the series. So the same series, I don't know why I did it all over there. The same series, except the absolute value. Okay, and just like with my limits, what that ends up doing is taking away the alternating part of it. Okay, so I just get rid of this -1 to the n. This is my series that I'm checking. Now I see that this is a p-series, which is divergent. Okay, so this is divergent. Okay, so with the absolute value, this is divergent. Without the absolute value bars, it's convergent. So this is what we call conditionally convergent. Okay, so it was convergent when it was alternating. It's divergent when it's not alternating, and so we call that conditionally convergent. Right? Okay, now one last thing. I just want you to be careful because this comes up a lot in, I don't know, like YouTube. I've seen a lot of videos of stuff like this where you can kind of come up with some crazy things just by rearranging series. Okay, so if you have a conditionally convergent series, you can rearrange it to really equal any number. And so that kind of makes these dangerous, and so order does matter there. Okay, with absolutely convergent series, you can rearrange it and it doesn't matter. Okay, but with conditionally convergent series, order does matter, and so you have to be careful that you write it out in order just like this. Because what can happen is, say we have our given series here. So this is the alternating harmonic series, right? Now it goes like this, and you know, if you add all these up together, you get natural log of 2. Right? Well, say we just group these terms here. So I haven't really done anything different yet. All I've done is add parentheses right here, here, and here. Right? This will still equal the natural log of 2. Okay, well, say we actually evaluate then. So 1 minus 1/2 is 1/2. Okay, the 1/4 stays. 1/3 minus 1/6 is 1/6. The 1/8 stays. 1/5 minus 1/10 is 1/10. The 1/12 stays, and the 1/7 minus 1/14 is 1/14. All right, I haven't really changed much, but all of a sudden it looks like I'm missing a term. Okay, so I mean, this will probably still equal the natural log of 2. But then all of a sudden, so I was missing my first term, and now what I've done is I factored out a 1/2. Right, so if I factor out a 1/2 from every term, and keep in mind this is infinite, so it goes on to infinity. There's an infinite number of terms I'm factoring a 1/2 out of. I have a 1/2 out front, and on the inside of my parentheses, I have what looks to be the alternating harmonic series again. All right, just like I had up here. It looks like I have the alternating harmonic series again, which I know the value of my inside here is natural log of 2. So the 1/2 is just the 1/2. So like, where did the 1/2 come from? I just brought that out of nothing, essentially. Right, so you have to be careful with these, with conditionally convergent, specifically conditionally convergent sums. You have to write them in order, or else crazy things can happen. All right, so just be careful with that. You can be skeptical if you see crazy videos on YouTube. Just saying. All right, that's it. See y'all later.